Um, okay, now let's begin the second session. So, in the previous question, we specified the charge on the boundary, and now this is slightly different, and it's actually a more physical question. And so this question is saying that here suppose there is a background electric field pointing upwards towards the z direction. So if there is no metal sphere, then the electric field will be all be straight lines pointing upwards. And now in this background electric field, we add additional metal sphere. And what this metal sphere does is that it enforces an equipotential surface at the surface of this metal sphere. And you can kind of imagine that because of this metal sphere, the electrons at this conductor can move freely. So what happens is that under the electric field, the electrons, positive electrons, will go upwards, and so there will be a charge accumulating on the top. And meanwhile, there will be negative charge accumulating on the bottom until a very exact moment such that the upwards charge and the downwards charge form an exact balance. Then inside of this sphere, the electric field will be zero, because that's what's required by the conductor. So in this problem, there will be a very particular distribution of the induced charge on the surface. Right now, we are still not sure about this, but there has to be some positive charge over here and negative charge over there. And this problem is special in the sense that it actually has azimuthal symmetry, because if you rotate this system around the z-axis, the problem remains unchanged. And now if you do this problem in the spherical coordinates, then you can apply what we just learned about the spherical Laplace equation. So what we have for the potential must be written like this, and but this is the general solution, and we still need a boundary condition. So let's try to analyze the boundary condition for this problem. So there are at least two boundary conditions, right? So anyone has any input? So could you tell me what's like the boundary conditions? So this is actually debatable, because we have in this problem, it's a special problem that there is a field pointing upwards. So in this, let me try to write down this field. So imagine there is the electric field always pointing upwards. Then the potential should be an integral of this E field, and you can see that there must be some potential gradient when you are very far away, right? So when it's very far away, the potential, the E field must be given by this expression. So if we look at the potential, that's simply say that from 0 to z. And if you do this integral, I think there is a minus sign, and then this should be actually so you can see that the potential must be decreasing as you go along the z-axis. And so actually for this special problem, the potential is not 0, but takes a very strange form, like over here. So this is now we figure out one of the boundary conditions. So the other is actually kind of easy, because we have a metal sphere, right? And then at I equals 0, and the potential must be 0. Sorry, at I equals capital R. So the question is to fit to these two boundary conditions. And now this z, if we can express this z in terms of r cosine theta. And so this is simply a transformation from Cartesian coordinate to the spherical coordinate. Now what we need to do next is to apply this two boundary condition to the problem over here, to the general expression over here. So let's apply the boundary condition for let's apply the first boundary condition. So let's take the value at r equals capital R, and that gives now the second boundary condition is saying that when r goes to infinite, it takes a value of minus E naught R cosine theta. But let's first take a look at the general expression. So here, the general expression is something over here, right? So we just said earlier that for a typical boundary condition with R infinity goes to 0, we simply ignore this term, because this term will diverge. But here, in this case, you can see that the boundary condition is, actually has the r to the power of 1. So not every one of these terms goes to 0. You can see that we somehow have to keep a1. And for b, for BL it can be there, but for AL it must be Okay, we haven't deal with the first boundary condition yet. So if we look at the first boundary condition, then this simply gives the relation like this. So here, if we express the BL in terms of AL, the BL must be R to the 2L plus 1 power times negative AL. Now from the second expression, we know that only A1 is something that's non-zero. So here, for this BL, so only the B1 is non-zero, which means that the solution should be A1 A1 then should be R, the L equals 0, E1 over R2. So this should be a general solution, and now let's match this with the boundary condition. Here, this P1 cosine theta is simply cosine theta, and here this B1 must be minus R to the power 3 of A1, and we should evaluate the position at R equals R. So this gives us A1 capital R minus R to the power of 3 over this is evaluated as infinity. So then this gives the second term in the boundary condition simply vanish, because when R equals infinity, this term does not participate in the boundary condition. So this means that A1 R cosine theta must equal to E0 R cosine theta, and A1 must be minus E0. Now the final solution should be B minus E0 R cosine theta plus B1 over R to the power of 2. So the B1 is R cubed E0 and you see that here the first term, so this should be our final solution, and the first term is exactly identical to the boundary condition we specified here. So the first term means that this is the potential that's far away from the metal sphere, and then there is the additional term. This term should be the potential that's formed by the metal sphere. And another way of putting it is the induced charge on the surface of this metal sphere is responsible for this additional potential V. So this second term. And now let's take a look at what is the induced charge. So the induced charge, again, formula. The formula for the induced charge is somewhere that we've already given in the previous lectures. So the induced charge should be proportional to the electric field perpendicular to this metal. And if we translate that to the potential, then this should be the potential gradient, or the potential along the derivative of the potential at R. And if you evaluate this term, it will give you So my question for you is, here we have two terms for the potential, right? And what I just said, that this term is responsible. This term originates from the electric field far away, and this term is responsible. This term is produced by the induced charge. And so my question is, here for this V, shall we use the V over here, the total V, or shall we use the V here that's subtracting this background electric field? So shall we use, let's denote this as V2 and this as V1. Shall we use V total that's equal to V2 plus V1? Or shall we plug in this V2 here for this when you are calculating the induced charge? Okay, any difference? So I get one answer is to use the total. So any other opinions? Yeah. So the answer is like actually both of these two works. So the reason is that this term actually does not have any induced charge. So if you calculate the derivative of this term, it will it should be giving you 0, and you shouldn't see any charge distribution caused by this term. So either way is fine. So I think you can use this one or use the total.
But the external field physically say will induce charge also.
Yeah, yeah. So this term, so it's the external field that induces a charge distribution, and this induced charge distribution produce additional V over like this. But when you are trying to calculate this, when you are trying to calculate the induced charge distribution, I think you can use either the total one or this one. So, but you can try to do this at home to see if what I'm saying is correct, and I might be wrong. Okay. Now let's try to plot. So in principle, this V should be the total V. But my feeling is that if you use V2, it's still okay. So now let's take a plot of this sigma distribution as a function of theta. So that is simply the cosine theta function. So at theta equals 0, the sigma reaches the maximum value, and because the cosine theta 0 is at 1, and then at theta equals pi, it reaches an equal but negative part. So if we plot this sigma as a function of theta, then the function looks like this. So what this means is that now let's take a look at this sphere. So this means that there will be the most positive charge on the north pole, and the most negative charge on the south pole, and exactly at this equator there won't be any charges. So now this complicated charge distribution actually has been determined by us. Okay, so let's have a look at the last question. So the last type of question that you might see is that sometimes the potential might not be specified everywhere, anywhere. And so for this example, you see that instead of specifying the potential, somehow here the charge density distribution is specified. So again, it's a shell of the sphere, and with radius r. So the surface charge density, say given, is a constant times the cosine 3 theta. And now it's asking what should be the potential inside or outside the sphere. So this problem is well defined, because once the charge density is given, then the E field should be given everywhere, and that's by definition the Poisson's equation. And right now we are not trying to use the Poisson's equation, but try to use Laplace equation to solve this problem. So the difference between the Laplace equation and the Poisson equation is that when we are looking at the Laplace equation, the area of interest cannot have any charge. So for this problem, we have two different regimes, right? So one regime is what's the inside. Another regime is the completely outside this sphere. So let's have a look at both regimes. And now let's write down the potential inside. So based on our previous example, the potential inside must be written as a form like because here the 1 over r to the L plus 1 cannot appear inside. And now let's check what's outside solution. And so what is still unknown is the AL or the BL. But we can somehow still relate the AL coefficient and the BL coefficient, because of two of these conditions. So one condition is that the potential must be continuous. So here Vi at R equals R, capital R, must be the same as the Vi at, the V out at R equals capital R, which means that here the AL that this looks reasonable to you, or looks trivial to you, or
There is a difference for the contribution for only V1, it's only V2 and total potential. The intense charge.
we can discuss this problem maybe later. Yeah. So let's take a look at this problem. So here at I equals to R, the boundary condition claims that the AL, the inside potential must be continuous with outside, and what we arrive is that AL R equals L equals BL over R equals L plus 1. But is this does this looks trivial to you, or would you say that there's actually more subtleties into this conclusion? So I would say that there are some subtleties in this derivation, because when you are trying to relate the two, you are relating a sum to another sum, and so what's on the left is this sum over PL cosine theta, and on the right is another sum over PL cosine theta. You really have to use the orthonormal relations. So in principle, you have to do the integral over this expression and the P0 cosine theta, and then get the matching condition for the A1. And then you have to do again for this P1, and then do an integral on the left and on the right, and then compare, and that will arrive you the A2 and the B2. And after you doing infinitely many of this, you can get the final expression here. And the way that I say that it's trivial here is because I tried the method by simply eyeballing or simply by inspection. So that is trying to look at the problem into in different components, and we have to match the boundary condition on each of these components. But mathematically speaking, this argument, you have to really to use this orthonormal relations to guarantee that what we just did is okay. And now the second condition is that the normal derivative of this system should be discontinuous. And this discontinuity is actually defined by this charge. So this is this one is the general expression for given surface charge, and what's the relationship between the derivative of the potential and the surface charge. So remember that I try to give analogy to the quantum mechanics. So this is the way we use it here, that as long as there's a surface charge, we can treat that similar to a delta function, and this will cause the potential, the value of the potential to be smooth, but the derivative of that to be discontinuous, and the discontinuity is specified by this amount of the surface charge. Now, if we plug this everything in, we simply get now let's take rearrange the terms. So we try to plug this expression for the BL and re-express the BL in terms of AL. So BL equals 2L plus 1 times AL, and if we plug that in, this one gives and these two terms actually combine together to give 2L plus 1. Now we simply need to repeat what we did by doing integral of 0 to pi and PL prime and cosine theta, and also remembering this sine theta and d theta. Let's apply this both to the left and to the right, and you will arrive at this so here this sigma naught is k cosine 3 pi, 3 theta, and there is this trig identity that the cosine 3 theta actually equals to 4 cosine theta cubed minus 3 cosine theta. So you need to be able to derive this by yourself, and in the homework you will also see this expression, and so it's just a reminder that you have to derive this in the homework. And now if you plug this in, you can actually also try to eyeball your solution by simply comparing this cosine theta to this to the expression for this Legendre polynomial, because here p cosine theta equals cosine theta, and p3 cosine theta equals 1/1/2 5 cosine theta cubed minus 3 cosine theta. And if so, this means that this term should be composed of P1 and P3 only. And if you do the calculations, I think you will arrive at the surface charge. So you can obtain this expression either by directly comparing with P1, P3, or you do strict integrals for this L equals 1, L equals 3. And anyway, you should be able to get this expression. And in the end, if you do the Fourier's trick, you get so that gives you the final solution to this problem.